Hello class, welcome to Pre-Algebra section 11.5. Last class we talked about quadrilaterals and the different types of quadrilaterals we have. And a quadrilateral is just one kind of polygon. So a polygon is a simple closed figure formed by three or more coplanar line segments. And this word simple right here is just telling us that it's composed of straight lines. That's what simple is telling us. So if we ever see a shape with a curved figure, then it's not going to be a polygon. And all of these line segments meet together at the vertexes, and the polygons are classified by the different number of sides they have. So if we look over to the right, we see a polygon with 3 sides is a triangle. 4 sides is a quadrilateral, which we talked about last class. So we're going to look at our first example, and we're going to determine whether the figure is a polygon or not, and we're going to classify what type of polygon it is. So our first figure, we have 1, 2, 3, 4, 5 straight lines that all meet and create a closed shape. So we can go ahead and say that, yep, this is a polygon. And now we just need to determine what type of polygon it is. If we look back up at our table, our polygon has 5 sides, so it's going to be a pentagon. So we can say, yes, this is a pentagon. Our example B, it's a little bit different. We've got a curved shape here, so immediately we can tell that, nope, this is not a polygon because it has the curved lines. So let's scroll down and take a look at our next couple examples we have here. And I'm going to let you guys do the first one on your own, but I want to talk about the second one because the second one has a new term to it. So let's determine if this is a polygon or not. Well, it's a completely closed figure by straight lines, so we can go ahead and say, yes, this is a polygon. Now, what type of polygon is it? It has 1, 2, 3, 4, 5, 6, 7 sides. So if it has 7 sides, we can scroll up and see that it is 7-sided figure is called a heptagon. So we know that this is a heptagon, but it is also what we can call a convex heptagon. And we'll talk about what convex means. Convex is whenever our shape points out. So if you can see here that this comes out and makes somewhat of a triangle over here, right? Well, if it's pointing out away from the figure, we call it convex. But if, say we were to have a shape that looked like this, where it comes into the figure, we would call that concave. So we can have a convex or a concave figure, polygon. So you guys can go ahead and do number 3 on your own, and we'll flip over to the next page. Now that we know there's a number of different polygons based on the number of sides they have, we can use the number of sides they have to find out the measure of the interior angles of the polygons. So we've got a couple new terms here. The first one is a diagonal, and a diagonal is any line in a polygon that joins 2 consecutive vertices. So if we look at our model down here, they've shown us 3 diagonals in this hexagon. And these are diagonals because they're connecting one vertice to another vertice, one vertice to another vertice. And so when we make these diagonals, it splits our hexagon into 1, 2, 3, 4 different triangles. And so we can use those triangles to find the sum of the interior angles of the entire hexagon, because we know the sum of the interior angles for a triangle is 180. Since we have 4 triangles, if we multiply that by 4, then the sum of our interior angles of the hexagon is going to be 4 times 180, which is 720. So the sum of our interior angles of this polygon is going to be 720. So one thing I want you to notice is this was a hexagon. How many sides does a hexagon have? It has 6 sides. But we didn't multiply 180 by 6, we multiplied it by 4. So as we can see from our formula over here, if we take the number of sides, which is represented by n, for our example we had 6 sides, we subtract 2 and multiply that by 180, that'll give us the sum of the interior angles for all of the polygons we want. So 6 minus 2 is 4, times 180 gives us what we found, 720. So we can use that formula for all polygons. But before we use this example, before we use this model for different polygons, I want to talk about what a regular polygon is. And a regular polygon is a polygon that's equilateral, so all of the sides are the same length, and it's equiangular, which means all of the angles are congruent. So right here in our example, this is not a regular polygon because this side here is not the same length as this side here, and this angle right here is not going to be the same as this angle right here. So let's move on and take a look at our first example. In our example, they want us to find the measure of one interior angle of a regular non-gon. Of a regular 20-gon, I'm sorry. So a 20-gon is a polygon that has 20 sides. So we can use our formula that we just learned to figure out the measure of the sum of the interior angles. So we can find how much all of the angles together add up to by using our formula. So we're going to do n is going to be 20 because it's the number of sides, minus 2 times 180 is going to give us 18 times 180, which is 3,240. So we got 3,240. So 3,240 is the total number of the interior angles, the sum of all of the interior angles. And since it's a regular polygon, we know all of the angles are equiangular, so they're all the same measurement. So if we do 3,240 divided by the number of angles, which is going to be 20, a 20-gon has 20 sides and 20 angles, then we can find out exactly the measure of each angle. So 3,240 divided by 20 will tell us that each angle is 162 degrees. So this gives us a new formula for regular polygons. So for a regular polygon, we can use the formula n minus 2 times 180 divided by n, and that's going to give us the measure of each angle. So let's scroll down and take a look at our next example. We want to find the sum of the measures of the interior angles of each polygon. So we're going to do a quadrilateral first. A quadrilateral has 4 sides. So if we use our formula, 4 minus 2 times 180 is going to give us 2 times 180, which I believe is 360 degrees. So the sum of all the interior angles is 360 degrees. And that's all they're asking for us in this problem. They're not asking for each angle, they're just asking for the sum of all the angles. And they're doing that as well for number 2, 3, and 4. So I'm going to let you guys do 2, 3, and 4 on your own, and I'm going to scroll down and work on 5, 6, and 7 here. So with 5, they're asking us to find the measure of one interior angle for each of the polygons. So now we know it's a regular polygon, a regular pentagon, so each of the angles are the same measurement. They're all congruent. So we can use our formula that we talked about earlier. We can do 5, the number of sides, minus 2 times 180. That will give us the measure of all the interior angles, and if we're looking for each angle, we're going to divide that by the number of angles, which is 5, and that will end up giving us 108 degrees for each angle. So you guys can go ahead and knock out number 6 and number 7. You'll be doing the same process. So you guys can work on those, and if you have any questions, bring those to class and we can answer them tomorrow. See you.